In this video, I'm going to do another combustion analysis example, but this one's going to be a little bit different, a little more complicated, because we're going to take a compound that's still a hydrocarbon, so it still has carbon and hydrogen, but now it also has oxygen in it. So it's still a hydrocarbon, but it's got this extra piece to it. We know that this is going to be a combustion analysis problem because it has our hydrocarbon and it actually says combustion analysis. And as soon as we know it's combustion analysis, we know it's essentially an empirical formula problem. So combustion analysis, I always like to write the reaction first so I can kind of visualize what's happening. So in this case, we have that hydrocarbon with a carbon hydrogen plus the oxygen piece to it in that original substance. It's combustion, so we're going to react with oxygen and we're going to make H2O and CO2. So this is always given whenever you have a combustion analysis problem. They tell us that we're starting with 1.516 grams of this, and we're going to end up with 1.705 grams of water and 2.082 grams of CO2. So in the previous example, we said that if it's combustion analysis, the nice thing about it is that I will know how much water and how much CO2 I have. And all of the hydrogen in that water is going to come from the hydrogen in my original compound. All of the carbon in the CO2 is going to come from the carbon in that original compound. So I can take this mass of water, find the mass of or moles of hydrogen, and know that that's equal to the moles of hydrogen here. I can take the mass of CO2, find the moles of carbon, and know that that's equivalent to the moles of carbon here. This case, we also have oxygen, and the oxygen makes it a little bit more complicated because I need to find moles of this oxygen, but I have oxygen all over the place. So we have oxygen in the water, we have oxygen in the CO2, and even though I could find the total amount of oxygen in the product side, so I could find the moles here and the moles here and add those together, I can't do the same thing and say that all of that oxygen comes from the compound I started with here because I have this extra oxygen here and I have no idea how much of this I've added. So we're going to have to do something a little bit different to identify the moles of the oxygen. I do want to just set up over here just that mental check of what my goal for this is. So I need moles of carbon, I need moles of hydrogen, and moles of oxygen, right? It's always nice to kind of remind yourself what you need to find. So for an empirical formula problem, I need moles of each of those things. So let's go ahead and do the carbon and hydrogen, and we'll come back and revisit the oxygen. So the carbon and hydrogen, we're going to do the same way that we've done before. So I'm going to find moles of carbon just using my CO2. So we're going to start with that 2.082 grams of CO2. So that gets me to my moles of CO2. I'm going to do this extra step, which is just this 1-to-1 ratio. So if you're covering that in your head, that's good. It's just always nice to do that kind of mental check and make sure you thought about that. So this is going to give me 0.04731 moles of carbon. Then we can do similar approach to find our moles of hydrogen. We're going to use that mass of water. So we do molar mass of water. And then this one, that next step is a little more important because we want to remember there are 2 moles of hydrogen in every 1 mole of water. So it's more important that we do that for that hydrogen. So this gives us 1892 moles of hydrogen. So if this was just a basic hydrocarbon with carbon and hydrogen, that would be our first step. Next step would just be ratio these two, and we'd end up with our formula. So we have moles of carbon and we have moles of hydrogen. But we do need to figure out that moles of oxygen. And as I said earlier, we have to use a little bit of a different approach here to do that. So what we want to do is recognize that I do know how many moles of this I have, and I know how many moles of this I have. And I have a total mass here. So if I know the moles of carbon in this compound, I can figure out the mass of this carbon. If I know the moles of hydrogen, I can figure out the mass of this hydrogen. And if I know the mass of both of these two things together, and I know the total mass, I can subtract those two numbers and find the mass of oxygen. So we're going to take this moles here, we're going to convert that using molar mass to get grams of these carbon, of the amount of carbon in the compound. We're going to take the moles of hydrogen here, convert that to grams. So I'm going to have the grams of this piece or these two elements in this compound, and I'm going to subtract that from my total. So our next step, I'll call this step 1, is to find moles. So when we do an empirical formula with oxygen, I'm just going to call this 1B. So we have this kind of intermediate step. So we need to we're going to find grams of C and H. So we're going to take those moles. So I'm going to look for grams of carbon. So I'm just going to take those moles we found above and use molar mass to find those grams of carbon. And this is going to be 0.5682 grams of carbon. Then we're going to use those moles of hydrogen to find grams of hydrogen. Again, just doing molar mass here. And this is going to get us 0.1911 grams of hydrogen. So if I know the mass of carbon and the mass of hydrogen, I'm going to add these two together, and we're going to get 0.7593 grams, and this is hydrogen plus carbon, right? So this is the mass of the hydrogen and carbon in our starting compound. So I now found the mass of this. So I need to subtract that mass from my total to get me my mass of oxygen. Once we have mass of oxygen, then we still need to convert that to moles. So we still have a couple of extra steps. But I'm going to take this number here, this 1.516. So I'm going to put that down here. So we have 1.516 grams. So we're going to subtract this here, 7593. And we're going to end up with 0.7567 grams of oxygen. Okay, so again, what we did here, this was total mass. This here is the mass of the carbon and hydrogen. So whatever is left over is the mass of our oxygen. So we're going to go ahead and take this number now, convert that guy to moles. So we need moles of oxygen. So we're just going to divide by that molar mass. And we're going to end up with 0.04729 moles of oxygen. And now we have all of our different moles. So we have moles of oxygen here, we have moles of hydrogen, and we have moles of carbon. So we finished kind of that first step. I'll go back and check that off here. We got moles of oxygen. So now we just need to do our ratios. So we want to go ahead and take everything and divide by the smallest number. So if we look at our numbers, I'm going to zoom this out a little bit so we can see everything together. If we look at our oxygen and our carbon, so those are pretty close together. So if we look out to our, let's see, our third and fourth decimal position, these are pretty close together. So that oxygen and carbon is going to be a 1-to-1 ratio. So the only thing I need to ratio essentially is this hydrogen to either the carbon or the oxygen. So if we take that hydrogen to the oxygen, this is going to be a 4-to-1 ratio. So let me go ahead and do that down here below. So we're going to take that 0.1892. This is moles of hydrogen over 0.04. I'll just use this number here. 729 moles of oxygen. So this is 4 moles of hydrogen for every 1 mole of oxygen. So this is step 2. Step 3 is just to write out our formula. So our formula is going to be carbon, hydrogen, and oxygen. So carbon and hydrogen are in a 1-to-1 ratio, and then our hydrogen is a 4-to-1 ratio for each of those together. So again, if we just look back at what we did here real quickly, so it's still a combustion analysis problem. So we start by thinking about that combustion reaction. I need to find the moles of each of these elements in that original compound, the hydrocarbon compound we're interested in. So we use the water and CO2, the mass of each of those, to find the hydrogen and the carbon. If I have oxygen in my starting compound, then I'm going to have to do this extra step where I take this mass of, or the moles of carbon and moles of hydrogen, convert those to masses to figure out what the mass of that part of the compound is, subtract those two to find the mass of the oxygen, convert that oxygen into moles, which we did right here, and then go back and just finish our empirical formula process where we ratio the moles of each substance and then end up with our final compound.